Okay, welcome to our first video about carbohydrates. And as we start this video, we are going to be looking at the nomenclature and the structures associated with this class of compounds. And so I want to start by comparing the two terms carbohydrate versus saccharide. Um, and really, the carbohydrate term is the older term. It came from this idea that the general formula for many carbohydrates is carbon with water. So carbohydrates have at least one carbonyl and at least two of those alcohol groups, our OH groups, okay, hydroxyl. When you hear the term simple carbohydrates, they're talking about monomers or dimers, so one unit or two units bonded together. And as we talk about complex carbohydrates, we're talking about polymers, which we can also call glycans. So if we scoot to the right, saccharides mean all the same things as carbohydrates, but it's a broader, more technical term. So a saccharide would still have at least one carbonyl and at least two hydroxyl groups. All right, we're going to use a little bit different terminology. Monosaccharide is that monomer unit. Disaccharide clearly is the two units. Oligosaccharide is a short, small group versus polysaccharide, which can have hundreds to thousands of units. And we're going to look at those monomers and polymers. And this saccharide can also include derivatives of carbohydrates. So molecules that are based on a carb, but where a hydroxyl or carbonyl has been substituted for something else. So for example, you might have an amine group where a hydroxyl group normally was, or maybe a phosphate group or a sulfate group added on there. And so those are called derivatives. They're based on carbohydrates, but they have that added piece. All right, let's start with those monosaccharides. So as we talk about these are the simplest carbohydrates. They will be either aldehydes or ketones. So remember, that's because of that carbonyl group, right? And if we come down here and look, we can see that depending where that carbohydrate, so the smallest ones will have 3 carbons, or depending where that carbonyl is, here it's right in the middle. So this is a ketone group, but in both of these, it's on that end carbon, so we have an aldehyde group. So let's talk some terminology. Notice that we're calling this a ketose. That's because of where that carbonyl group is. It came from that ketone. And notice we're calling these the aldose, and again, it's because that carbonyl is on that end group. We have an aldehyde group. We could also call this a triose. So that OSE is giving us that sugar piece, talking about it being a carbohydrate, and triose because it's 3 carbon. We'll oftentimes see pentose or hexose sugars, 5 or 6 carbons. As we look over here on the right, we'll see that we have the D and L piece, and we're going to come back and talk about that, right? That's because we have these chiral carbons right here, and so D and L, they can be those mirror images. All right, and by the way, in nature, the D form is the preferred form, the dominant form. And so often we'll leave that D out. It's assumed that it's the D form unless it's otherwise noted. So we would always put the L, but we might leave the D out. All right, onward. We want to take a minute and talk about this nucleophilic addition reaction where we have an alcohol reacting with an aldehyde, okay? And so we have this addition reaction where the oxygen acts as a nucleophile, all right, and attacks, and we get what we call hemaacetal, um, where we have this group here from our aldehyde bound through that oxygen to the group from our alcohol. All right, so oxygen's the nucleophile. It attacks that carbonyl group. The electrons, so this attacks here. These electrons come out here and can grab the hydrogen. And we see these reactions. And the reason we care about these is because when we think about our carbs, we have both of these groups. Notice that our groups that were important here was this carbonyl and this alcohol group, right? This hydroxyl. Well, here we've got glucose, and look at that. We got a carbonyl, we've got a bunch of hydroxyl groups, true? And so what we'll have is we have what we call an intramolecular hemaacetal or hemaketal. And this simply means that the R group of the alcohol is already covalently attached to the R group of the aldehyde. And so this sugar cyclization reaction happens, and we see that we end up with these cyclic compounds, okay? And we'll step through this several times today. Interestingly, these are not catalyzed by enzymes. They occur spontaneously and reversibly in aqueous solutions. And for these 5 and 6 member rings, we find that the ring structure is the more stable one. It accounts for almost all of the structures in equilibrium. All right, so when we look at this, let's talk a little bit about some terminology and how this happens. So this carbon right here is the penultimate carbon, the next to the last one. And if you think about it, it is the last one with a chiral center, okay, or stereocenter. So this carbon right here, whoops, I wanted a different color, right there is that penultimate carbon. And that one is going to have the hydroxyl group. So this whole thing's going to bend around and come up here and attack different color, this carbon right here. All right, and that's what we see over here on the right. And notice that we've colored these, right, so that we have this oxygen in red. We see is now it's wrapped itself all the way around and it's here and it's attacking this carbon. And then that carbon's oxygen is shown in green here. And as that happens, this oxygen comes around, attacks, gives away its hydrogen, and it becomes the oxygen in the ring. This carbon is the next one in the ring, and it did have a double bond to this oxygen, but now it's going to, as it forms this new bond, these electrons will come out, grab the hydrogen, and it becomes that OH group. And so we end up with 2 possible structures with the OH going down or up, and we're going to come back and talk about that. The carbon that had the carbonyl, the carbon that was attacked by the penultimate carbon, is our anomeric carbon. Okay, and that is another one that we will talk about. All right, so as we look, we have our Fisher projection over here on the right, this kind of straight chain. We have our Haworth projection right here, showing our ring. And we know that really that ring is kind of in this chair conformation, but we will very oftentimes draw it this way. All right, look at this next one. Isomers. So let's talk classes of isomers. Isomers have the same molecular formula, but different structures. The easiest type to identify is a constitutional isomer, okay, because these things have different orders of attachment. So for example, here, the carbonyl is on the first carbon. Here the carbonyl is on the second carbon. Two different molecules. What we will often look at are stereoisomers. So now the atoms are connected in the same order, but the way they're arranged in 3 dimensions is different. Okay, so we'll have chiral centers where carbon's attached to 4 different things, and the arrangement of those things is different. Now the first one we can look at over here in enantiomers are those non-superimposable mirror images. So if you pictured putting a mirror down here on this plane between the two, we can see that the one on the left and the one on the right would be mirror images. If we could fold them in, right, it would be like looking in the mirror. But we can't just drag this one over the top of this one. Those will not line up. So they're non-superimposable mirror images. If we look at this, all right, these are both glucose. And let's talk D versus L naming schemes here. We are going to base that. So in our Fisher projection, we're drawing it with our carbonyl towards the top, and we're going to number these. So we would have our numbered carbons 1, 2, 3, 4, 5, 6 right here. And the chiral carbon that is as far from the carbonyl group as possible is going to be the one that determines the D or L. So if I am looking here, that carbon, that chiral carbon, because that carbon 6 is not chiral, that chiral carbon that's as far as possible from the carbonyl would be carbon 5. And generally, it is going to be that penultimate carbon. And then when I look at this, if I have the OH on the right, it's going to be the D version, so this is D-glucose. If instead I've got that chiral carbon and my OH is on the left, that would be our L-glucose. All right, so we're looking for the penultimate carbon, or the last chiral carbon as far from the carbonyl as possible, and determining is the OH on the right or the left. That's going to determine if it's D or L. All right, so that's enantiomers, non-superimposable mirror images. Let's keep going. Diastereoisomers. So these are isomers that are not mirror images. So let's look at the 2 examples here. And if I start looking, I can see that down here, oh, these are the same, oh, but now when I get here, the arrangement around those is not the same. Okay, and then when I look up here, the arrangement here is not the same. And when I look at this, though, because those bottom 2 are the same, top 2 are not, if I was to put a mirror down the middle and fold those in, they would not be mirror images. So now I have same order of connection, different 3D arrangement, but not mirror images for diastereoisomers. Okay, you do not need to memorize these names. You should be able to figure out if they are D, both of these are D actually, D or L. All right. Now, as we talk about diastereoisomers, there are some subclasses we can talk about. One is epimers. So these are going to differ at one of several asymmetric carbon atoms. So as we look at this top one right here, let's see. So they differ here and here. So again, they're not mirror images, and they differ at just one. We're going to call those epimers. And then another option is what we call anomers. So that should bring to mind anomeric carbon. And so this, we're going to be looking at the ring form here. And so let's take a look at our next slide so we can talk about this. All right. when we have a straight chain monosaccharide that forms a cyclic structure, that carbonyl oxygen, so remember, we're just going to, this penultimate carbon, the hydroxyl on that oxygen's going to attack the carbonyl. So here was this, here was our carbonyl, that number one carbon right here. When this attacks, this can get pushed essentially up or down. So we can come up with two different options. The one where that oxygen was pushed downward, or the one where the oxygen was pushed upward. So we have two different isomers, and we're going to call these anomers because they differ at that anomeric carbon. If we have, and I've got this written over here, so if we have an alpha anomer, it means the hydroxyl at that anomeric carbon, okay, right here, is opposite the side that C6 carbon. So let's number our carbons real fast right here. So number one would be right here, 2, 3, 4, 5, 6. All right. I oftentimes find it easy to think about it as I'm numbering it. I'll be like, well, I know carbon 5 was the one that had the oxygen that's now part of the ring. And I know that that carbon has hanging not as part of the ring, but off the side of the ring is the CH2OH group up. So this must be carbon 5. So you can number it that way too and go backwards. Be like, ooh, 5, that was 6, 4, 3, 2, 1. Okay? So in this case, if we have the alpha, they are opposite. And so when you think about that, right, think opposite, you can think trans. So they're on opposite sides of the ring structure. The beta form, on the other hand, we see that OH and that carbon that's outside the ring are on the same side of the plane of the ring, okay, or cis. And this can be important. So when this monosaccharide is in the cyclic form, that form may be recognized by enzymes that make linkages to make these polymers, and whether or not it's in the alpha or beta form might give you a different type of linkage and a different type of molecule. All right, let's look at a few common monosaccharides. You don't need to memorize these, but just for interest factor. Okay, so ribose is a 5-carbon sugar, and deoxyribose, which you will have heard of if you look at that, deoxy minus the oxygen. So look at carbon number 2 as we look at ribose versus deoxyribose. There's the difference. These are aldehydes, so they would both be aldoses if we wanted to classify them that way. Okay, pentose because 5 carbon. All right, along the bottom we have several common, so glucose, mannose, galactose. Let's take a look at fructose because on this whole page, fructose is the only one that is a ketose because it was a ketone. Now that carbonyl is not on that end carbon, but instead it's on the second carbon. Let's take a minute and look at what that does in our reactions. So we have our straight chain form over here at the left. But now, as we're numbering from the end closest carbonyl, we see that our carbonyl carbon is actually carbon 2. We're still looking at that penultimate carbon, the hydroxyl there, to do that attack. So it's going to wrap around this oxygen. It's going to wrap around and attack that carbonyl carbon, but now it's carbon number 2. We're going to see that same reaction where we form this bond. We kick these electrons up and they grab the hydrogen. But now we have a carbon hanging off both this 5th carbon, so carbon 5 is here, so this is carbon 6, and we have a carbon hanging off of that anomeric carbon. So this would be our anomeric carbon. Okay, if I want to number these again now, this is a little different, right? Because this was carbon 1, this was carbon 2, 3, 4, 5, 6. Okay, so now we get a 5-membered ring. We can still classify them as alpha or beta, right? So we said alpha was trans opposite. And when we look, it's always going to look opposite to this same one. We're looking, this one's on this side of the plane, and that other one over here on carbon 6 is on opposite. Okay, or they can be beta, which would also be cis. Whoops. All right, one more piece of terminology. So same type pictures here. We've got glucose, whoops, glucose. We've got our cyclic structure. And just the thing I want to point out on here is these are sometimes called pyranose because of their resemblance to this structure, this molecule. As I look at my 5-member ring, they are oftentimes called furanoses as a class of compounds, furanoses, 6-member rings, 5-member rings, because of their similarity to this. All right, let's talk a little bit about conformations. So as we think about the three-dimensional structure, and you will have looked at this in organic chemistry, we can get the chair form, where one of those points of that 6-member ring points up and the other one down. So picture your little lounge chair. Or we can have the boat conformation where they both point upwards, right, and make a little boat that could float. And in each of those, then, we have axial and equatorial positions for the hydroxyl groups and the hydrogen groups. And it turns out that in the chair conformation, right, that we get the axial positions occupied by the hydrogen atoms, and essentially it reduces steric hindrance. And so we just know that this is the conformation that is more likely to occur. It's going to be the more stable one. Okay, some more terminology. Glucose is what we call a reducing sugar. So when we look at this, we have our ring structure in equilibrium with our open chain structure, which will actually be in equilibrium with the other ring structure, right? So we have 3 things that could happen. We could have the alpha anomer, the beta anomer, and the open chain form. And to go from the alpha to the beta, we got to go through the open chain form. So the open chain form is a very, very small percentage, but because it is potentially in this form, that open chain form can react with oxidizing agents. All right, so if you think about an oxidizing agent, okay, or a reducing agent, we said it's a reducing sugar. So something that is a reducing agent causes something else to be reduced. So something that's a reducing agent causes something else to be reduced. So it itself is oxidized. So remember, lose electrons oxidation, gain electrons reduction. So if it is causing something else to gain electrons, it must be losing electrons. It must be giving them away. So what happens here, we can see that copper is going from copper 2 plus to copper 1 plus. Its charge is going down. It must be gaining electrons. So our sugar must be losing electrons. So that means it must be oxidized. You can see right here Okay, it gains that oxygen. It is indeed oxidized. Um, this was, for example, this was an old technique to test for the quantity of glucose in urine. It was looking for essentially how much of one of these molecules there was, okay, this oxidized version of our glucose. All right, monosaccharides are joined to alcohols and amines through what we call glycosidic bonds. Right there. Let's look at an example. So we had here, this was an OH group on one glucose. Okay, here's my anomeric carbon. Let's change color. Right here is the anomeric carbon on that one. Here's the anomeric carbon on that one. Okay. This was also an OH group. And what happens is these two hydroxyl groups react and water leaves. So notice we lost OH and H. So water leaves and we end up with this linkage, all right, through the oxygen. So we end up with this linkage right here between the two. Okay, we call that an O. It's linked through the oxygen, glycosidic bond. I want to point out the way this is drawn can be a little confusing. They're trying to point out here that that bond goes downward from that plane, okay, because it turns out that that's important. But it makes it look as if there is a carbon right here, and there is not. Those were just OHs, and all that's left is the oxygen. So notice how I highlighted just in a V. So there is not carbons in kind of those elbows. It's just trying to show the directionality. Our anomeric carbon, we had a alpha linkage, right? Trans to this up here. And so this would be an alpha glycosidic bond. And we're going to look at that in a minute. We can also form, it doesn't have to be another carbohydrate that forms these bonds. So for example, right here, we had an OH group on our sugar molecule. And then we had an NH2 group on our amino acid. And again, what happens is water leaves, right? So we're losing the OH and one of these hydrogens. And now our linkage is through the nitrogen. So we have an N-glycosidic bond. Okay. Over here on the right, we're linking to serine, another amino acid. So we had an OH on this carbon, and we had our OH on that side chain. And again, water is leaving, so now we have another O-glycosidic bond. Okay. We can also form linkages to things like phosphates, so you can see the formation here with phosphate, and we'll be looking at that more later this semester. All right, y'all, let's look at a couple of common disaccharides, sucrose, which we're going to come back to in a minute. But let's start with lactose and maltose. If you look at these, so lactose is galactose and glucose. You don't need to know that, but just so you know, just so you've heard it, maltose is two glucose molecules. Now, when we look at this, and I identify my anomeric carbon in both, here's my anomeric carbon in the first one, and here's my anomeric carbon in the second one. So this linkage is like head to tail, the anomeric carbon of one to the opposite side of the other. Okay, when I look at this, my anomeric carbon, that's the one we mainly care about, my anomeric carbon was in the beta version, right? That hydroxyl was going up. So when we look at this, and did I get that right? Yes. So when I look at this, I'm going to expect this to be a beta 1,4. So our beta beta 1,4 linkage. So it's carbon number 1 on the first one to the left, it's carbon number 4 on the second one, and our anomeric carbon was in the beta form. When I look over here on the right, again, I've got my anomeric carbon, and when I look here, my anomeric carbon that's part of the bond was in the alpha configuration. This would be an alpha 1,4, first carbon on the left, fourth carbon in the one on the right. Let's look more closely at sucrose, because this one gets a little confusing. When I look at it, here was my picture of fructose before. Here's my anomeric carbon. The anomeric carbon, notice, has the hydroxide and the CH2OH group. But over here, it has just the CH2OH and the hydrogen. Let's compare this whole thing to what we have here. And what you'll see is that the one that has just the hydrogen is here. Essentially, we've had to flip this to form this bond. And what we see is that the anomeric carbon for the molecule on the left, okay, the glucose is forming the bond, and this is the anomeric carbon for the one on the right. As I look at whether these are alpha or beta, okay, for the sucrose, our OH was going down as compared to that group. For the fructose, our H is going down, but hey, that group too, because we flipped it. So the one on the left was alpha, right? So we used the alpha 1, and then the one on the right was beta, and remember, because it's fructose, it was the second carbon. Okay, so alpha 1, beta 2 linkage. All right, we'll do more of that, and we'll have some practice problems. The ones that would be more focusing on these. This one is a little more complex, and we could expect you to do this, but we'll do some more practice. All right, what about bigger things? Okay, so glycogen and starch are storage forms of glucose. Okay, complex carbohydrates, glycans, polysaccharides, lots of names for them. So when we look at glycogen, I'd expect you to be able to look at this and be like, hey, that's an alpha 1,4 linkage. Okay, alpha 1,4O glycosidic linkage, right? We got that oxygen. The interesting thing in these branching polymers is that we also get the alpha 1,6. We get some, we'll have a chain of these, and then we'll get some that start their own branches off of that 6 carbon. Okay, as we think about the glycogen, this is our storage in animals. Amylopectin is similar branched, and it is storage for plants. Okay, and amylose is also a storage. And now this is a linear structure, which provides some stability. It kind of forms these helices to provide that can pack together. The top two form more granules. All right, cellulose. So cellulose is a structural piece in plants rather than used for energy. Um, and we see these, now we have beta linkages. And the difference there is that those beta linkages lead to this straight chain capable of interacting with other cellulose molecules to form really strong fibers. Okay, that was a lot. At this point, you should be able to identify types of isomers by differentiating the structural details. You should be able to identify the anomeric carbon and the penultimate carbon. You should be able to differentiate different types of linkages and be comfortable with the nomenclature. All right, nice job finishing this one. Next video, we'll pick up here on more details about carbohydrates.